This is in PDF, right?
Yeah.
I don't know how you actually.
I think.
What are you trying to do?
Here. All right.
Right, you should be. Yeah, you're good to go.
Thank you. So, hi everyone. I will briefly talk about my part of work. Oh, okay. So I got to wear this thing. Makes me feel like Madonna. Okay. Is it good? Great. Okay, so I'm good to go. I will try to keep it brief because. This is sort of showcase on the electric usage side what we could do from the analytics perspective. The problem or our overall objective is to model, predict the energy usage, eventually to detect the trend anomalies, and ultimately we could do diagnostics. Okay, so I will showcase the part I did for electric usage for the HT and LT, but as you can see here, I try to design the scheme as a hierarchical modeling. You could apply to any level, so a national level, say here is a Tesco specific case. We could model the overall energy usage over all Tesco stores in Ireland or over UK. And then we can drill down to store level and apply similar analytics to pack level and the case level. One advantage of designing such a structure is you could start from any of these levels to drill down, okay, if there's a problem, where is the problem, to locate the problem and to do corresponding maintenance. All right, so for example, this is really after the data are collected and passed on to a person like me. What can you do about it? So here is the HT-LT aggregates over 34 Tesco stores. So HT is generally higher than LT. So the black lines is HT and the red lines is LT. It's starting from January 1st, 2012 to August of 2013. So you could clearly see the yearly cycles as expected, all right? So, and then you can see the HT and LT, they move together and show similar seasonal cycles. And HT has a stronger shifts in magnitude. The main level of the electric usage is not the only concern we have. If your electric usage oscillates too much, so the daily variation is too high, that should also cause a concern. Why things are changing so much, right? So here demonstrate the daily variation of HT-LT. So you could see that you have these peaks in summer, and same thing with LT, all right? So what causes these yearly cycles? One of the very significant factors is weather. Okay, so these two plots you could see here is, again, the aggregated HT on the upper one, and lower one is temperature. Here, clearly, the yearly cycle of electric usage of HT move together with temperature. When temperature peaks in summer, you have peaked usage, all right? So what else? This was to my surprise because I knew nothing about fridge in the past. Humidity also matters. You could see box plots here. So when humidity is low, lower than say first quintile, you could see the consumption is higher on average. And then between first and second quintile, it slightly decrease. And surprisingly, it's bouncing back when humidity is really high, higher than third quintile. All right, so this tells us that the weather really is the direct driven factor of the energy usage. Okay, I promise this will be the only formula I show today. So this is a model we use to model all the energy usage. It's a generalized additive model. There are many models out there you could use. One of the biggest advantage of GAN is you will see later on, it intuitively show you what happens in your data via these transfer functions. You could identify all the factors, the patterns, how they influence your energy usage. So, okay. The covariates we used to model the HT-LT is time of the day, time of the year, seasons. These are the calendar factors, and also temperature and the humidity. So these are the output of the GAN model, the transfer functions. Intuitively, this shows you the daily patterns of HT and LT. Okay, so this is on your x-axis, it's the time of the day. You could see that for LT, the minimum occurs around 4 a.m. And same with LT. So this is HT, this is LT. And the HT peaked around 5 p.m. and LT is slightly earlier, but 5 p.m. it's where LT is really high. So this transfer function really provides you with a visualization of what's going on, the pattern of your electric usage. And then further on, we could show how each weather factor is impacting your electric usage. So this is how your electric usage of HT react towards temperature. And this is to humidity. The effect of humidity is relatively mild compared to temperature. Temperature is pretty much a linear impact, okay? So, however, on the other hand, the temperature and humidity has similar impact on LT as well. So they are definitely significant, and this is how they are impacting our energy usage. So these two functions shows you the yearly cycle. As expected, it peaks in July. So July 10th is, I think it's hottest day. Yeah. So, and just want to point out that they are on different scale. HT is significantly higher than LT. Okay, so GAN fits very well. The fitted GAN could explain pretty much 97% of the variation. So as you can see, maybe not seeing so well, the black line is the actual HT and the red one is a predicted one. So it's pretty much all entirely overlaps the true value. If you zoom in this portion, that's what's going on. We're capturing really the daily peak and the daily minimum particularly well. So you could go not just at the store level, but drill down to the pack level and apply similar technologies. So here are 3 different HT packs. You can see that they really display a slightly different pattern. The overall pattern is similar. However, you can see this HT2 has a really discrete step change, right? So this is, if you aggregate all of them together, what happens. We can use GAN again to to predict your model. Slightly worse than before because it's a lower level of aggregation. Here is around 87% of the fit. Then similar as before, you could see the daily pattern of HT. And this tells you, for example, the peak occurs during from 11:30 to 6:30 p.m. And if you look at all the daily patterns of all the packs, it gives you a comparison. They are different. For the daily pattern and the yearly pattern, I suppose it's perhaps a bit more interesting because for one of the pack, they're all in the same story. So for one pack, it peaks in July, the other one in May, and the other one in June. So I suppose it has something to do with the operational. John can talk more about
Gas
this.
levels.
We still haven't solved that one, by the way.
Gas levels of the pack. With
gas levels.
yeah, could again, like when you, we've been looking at this for quite some time, and there's definitely something going on. It's either that or the other issue is we're not looking at the right pack. It's in a different country. But no, you're right. I mean, these are the sort of things that the engineering team would have been involved in to try and figure out, because these are the type of things we're throwing back to the guys and say, what's going on here? Because it's clear they're sitting next to each other, so what could it be? So this is the type of stuff we were involved in continually with work that was coming back on Bay and others or whatever. But yeah, absolutely, there's more questions asked than answered, but I guess somewhere along that journey you eventually get to an end point and be a lot more insightful and knowledgeable at the end of it than you were at the start, but accepting that you're never going to understand all of the variation.
And that's clearly beyond my capability. So the next few slides, I just want to quickly go through. After we gather data, what our analytical capability or in terms of data curation. This is a store from Green Yellow. This is a raw data we get from Green Yellow for a HT pack. Okay, so you could see there are missing data. There are certain patterns. After we get this data, what we do to start with is outlier detection. This is a purely automatic algorithm. So you could see they identify few outliers. We list the date. Usually we go further investigation to see what is going on these particular dates. A second one is the missing data. To detect the period of missing data and do simulation to fill the gap if we could. If there's a huge chunk of missing data, usually we don't do much because meanwhile you add bias to your data, right? So, and afterwards it's a trend detection. So you could really fit a cycle to see overall what is a general pattern of your data. And finally, you do change point detection. So you could choose how many change points you want to detect. So what are the significant change in your electric consumption you expect during the year? So here is roughly 10 of them. So you could see the different blue regime, how they are shifting around each other. So these identify the change point. And then that will cause the further investigation. Okay, that's ends for my presentation. Thank you.
Thanks, Brady.